Hi, in this tutorial I will give an overview of the mass spring damper system and how you can implement and simulate the mass spring damper system with Python. Before I start with the tutorial, I will give an overview of some of my Python resources. I have made different textbooks regarding Python. I have made a textbook called Python Programming, Python for Science and Engineering, Python for Control Engineering, and Python for Software Development. These textbooks and additional resources like videos, practical code examples, etc. are found on my webpage at this location. In this tutorial, I will give an overview of the mass spring damper system. I will provide simulations of the mass spring damper system using the SciPy ODE solvers. I will find the state space model and simulate the state space model. I will also find the discrete system of the mass spring damper system and simulate it. So here you see an overview of the mass spring damper system. The mass spring damper system is a typical system used for to demonstrate and illustrate modeling and simulation applications. So basically, the mass spring damper system consisting of a mass, a spring, and a damper. And then you can apply a force to the system, and then the purpose is to simulate how this mass is, what's happening with the mass when you apply a force to the mass, and depending on different values for the K. The K is the spring constant, C is the damper constant, and M is the mass of the system. And by applying Newton's second law, the sum of forces are equal to MA. And then we get the following equation for this system. We have the force minus the force of the damper, and the force of the spring equals to mx double dot, which is the acceleration of the system, A. So where t is the time, f t is the external force applied to the system, c is the damping constant, and k is the stiffness of this spring, and m is the mass, and x is the position of this object m. And then x, the derivative of x, and the first derivative of the position is the speed or the velocity of the object m. And the second derivative of the position x will then be the acceleration of the object m. So basically, this is the differential equation for the mass spring damper system that we will implement and simulate using Python. So then we have found the differential equation for the mass spring damper system. It's a second order differential equation. Typically we want to have the highest order derivative alone on the left side, so we can just put this on the left side and those on the right side, and then divide by m on the right side, and then we will have the following system, which is a second order differential equation of the system. Typically, when we are going to simulate it in Python, we typically need to have a system of first order derivatives. So we need to do this trick. You can set x equals to x1 and the derivative of x equal to x2. And then we get the following system. And finally, we will end up with the following system, which is a set of first order differential equations. So then we have the derivative of x1 equals to x2, and the derivative of x2 equals to f minus cx2 minus kx1 divided by m. So these are the two equations that we are going to use and implement and simulate using Python. So we will implement this mass spring damper system in different ways. Let's start with using this SciPy ODE solver. So SciPy is a free and open source Python library used for scientific computing and engineering. And SciPy contains modules for optimization, linear algebra, interpolation, image processing, and ODE solvers, which we are going to use now. And the SciPy Python library is included with the Anaconda distribution. So if you install Python through the Anaconda distribution, you get, in addition to Python itself, you get a decent editor called Spider. You get all the necessary Python libraries like SciPy, NumPy, Matplotlib, etc. So it's recommended that if you haven't installed Python, you can install it using the Anaconda distribution. So let's start with the Python code for the mass spring damper system. So basically we are going to implement and simulate these two differential equations, where x1 is the position and x2 is the velocity or speed of this mass. Then we will implement these equations, and we will simulate it by plotting the final result. So in this plot you see x1 is the position of the mass and x2 is the velocity or speed of this mass. Let's take a closer look at the code. We need to use the NumPy, so we import the NumPy library. We should also in this example use the SciPy and the submodule called integrate. So we import that module and that specific library as well, and we are going to plot it, so we also import the matplot library. All these libraries are part of the Anaconda distribution, so you don't need to install those libraries separately if you have installed Python through the Anaconda distribution. We need to have some initial simulation conditions, a start time and stop time, and then we can create an array of t values using the arrange function of the NumPy library. Then we can implement these differential equation as a Python function. I just call the function mydiff. We can of course call it mass spring damper system or something instead. And the input to this function is x, namely x1 and x2, and the t. And then we define some values for these constant. Damping constant, I just in this simulation I set it to 4. The stiffness of the spring I set it to 2, and the mass I set it to 20. And the force applied to the mass I just set it to 5. Of course, you can try with other values as well and see what's happening during the simulation. Then I implement these two differential equations just as they are stated here. Just note that x is an array, so x of 0 is x1 and x of 1 is actually x2. Then this function returns the result of these differential equations, and then I use the ODE int function, which is part of this SciPy library, and then the return value of this function is x, which is an array, two-dimensional array, where the first column is x1, or actually in Python the first or the 0 column is x1, this is the position, and then the first column is x2, which is the velocity or speed of the mass. Then I can use the matplotlib in order to plot the simulation results. So let's go to our Python environment. I will use the Spider editor in order to implement this simulation. So then I'm in the Spider editor, which is part of this Anaconda distribution. I start by importing the necessary Python libraries. I initialize the simulation. I want to simulate it for 60 seconds. And the initial condition for x1 and x2, I just set them to 0. And then, as mentioned, here I define the differential equations, x1 and x2. And then I use the built-in ODE solver in this SciPy library, ODE int. And input to this one is my diff, which is my differential equation. The initial condition of x1 and x2, which is an array of 2 elements, one for x1 and x2. And then we have the t, the time array, which I defined here. Then I want to plot both x1 and x2 in the same plot, and while the result returning value for this from this ODE int is 2-dimensional array with x1 and x2, so I just use this basic Python syntax in order to make an array with x1 and an array with x2, and then I can plot t versus x1 and t versus x2. I add some title, x label, y label, legend, grid, etc. And then we can click on this green arrow or F5 in order to run the simulation. And as you see, this is the result from the simulation. The blue line is x1, which is the position of the mass, and then this orange is x2, which is the velocity or the speed of the mass. So this is how you implement and simulate the mass spring damper system using this ODE solver in the SciPy library. Next, let's find the state space model of this mass spring damper system. So this is our starting point, our two differential equation, x1 and x2, and then you can set it on this general state space form, which is denoted like this. The derivative of x equals to ax plus bu, where a and b is matrices, x is an array or vector of x1 and x2, and u is the force applied to the system, in this case F. So then we get the following state space model. The derivative of x1 and the derivative of x2 equals to this A matrix, which is based on this equation. We have then 0, 0, 1, minus k above m and minus c above m. And then we have the x vector, x1 and x2, plus the B matrix, which will be then 0 and 1 above m. And then u, in this case, the control signal, if you may, or the force, in this case F. So now we have found the state space model of this mass spring damper system. So the next is to implement the state space model in Python and simulate it. I will use two different libraries in order to implement and simulate this state space model. The first library I will use is called Python Control Systems Library. This library is not part of the standard Anaconda distribution, so you need to install it separately. It's very easy to install. You just type pip install control, which is the name of the library. So pip is a package manager for installing Python packages. You find more information about pip and the package manager at this location. But let's just show how you can install this Python control system library using pip. So since I'm using Anaconda distribution, I just go here in Windows and start typing Anaconda, and then I will use the Anaconda prompt, which can be used to install additional Python packages. So then I just type here pip install install control, click enter, and then this control package has been installed and are ready to use. So let's go to our Spider, our editor, in order to implement this system. So here you see the code for the simulation. So I import, in addition to NumPy and the matplotlib, I also import this control library. I use this control library in order to be able to define the state space model and to simulate this state space model. So here you see the state space model of the system. So I define, as in the previous example, this damping constant, the stiffness of the spring K, the mass, and a force. And I also want to simulate it in the same interval from 0 to 60. I start to define these matrices A, B, and also in this case a C matrix. I just set the C matrix to, in this case, 1. I could set it to 1, 1, but 1, 0 means that the output of the system is just x1, which is the position. So then I use, as part of this control library, I use a function called SS, which is short for state space model, and the input or argument to this function is these matrices A, B, C. And we also have a D matrix, which is in this case is just 0. Then I can find and simulate this system using another built-in function in this control library called control.forced_response. And the input to this function is the sys, which is the state space model, T, this T array, and F, the force, which I set here, equals to 5. And then the output of this function is the T, Y, and X. And then I can use, as in previous example, this matplotlib in order to plot the final results. So now we are back in Spider. So in the first example, we implemented this mass spring damper system using SciPy and this ODE solver. And the name of the ODE solver was ODE int. In this example, we are going to implement the state space model. So I define ABC matrix and use this SS function in order to define the state space model. I have imported the control library in addition to NumPy and matplotlib. And then we use this control.forced_response function in order to simulate the system. And the input is the system, the state space model, the T array or the T vector, and the force F. And then I can plot it. So let's just run this example. And as you see, there's only one plot here, which is x1, or the position, since I'm plotting t versus y. But I can also choose to plot both x1 and x2. Then I can do like this. I can set x1 equal to x, the first column, and all values like this. Same with x2. Then x1, the first column, and then all values like this. And then I can instead of this one, I can plot t versus x1, and then t versus x2 like this. So let's just run the simulation. And then you see you got the same result as in the previous simulation. In the first example using this ODE solver in SciPy. So the blue line is x1, the position, and the orange one is x2, which is the velocity or speed of the mass. So we got the same result by implementing the system in two different ways. So I implemented the state space model of this mass spring damper system using this Python control system library. The problem with the Python control system library, it is not included with the Anaconda distribution, so we had to install it manually. It was not complicated. We just used pip, install, and control, name of the library. But we could have used the SciPy library instead. And the good thing about the SciPy, it's included with the Anaconda distribution. So now I will show you an alternative implementation of the state space model using SciPy. So in the SciPy library, have a submodule called signal, and in that module we have different functions for simulating continuous time linear systems. So we will use two functions, one for defining the state space model, it's called state space, and we will use the LSIM function in order to simulate the system. So here you will use the same state space model, and the Python code is almost identical. Instead of using the control library, we will import the SciPy.signal instead, and I just name it as an alias sig, and then we will use sys equal to sig.statespace in order to define the state space model, and the state space model is the same as in the previous example. And for the simulation, we will use the LSIM function of this SciPy library. And the input to this one is the system, the state space model, F, the force, which is equal to 5, and I just create an array of it using the ones function in the NumPy library. And this one has the same length as the t vector or array. And then we can just plot it using the matplot library as in the previous examples. So now we are back in Spider. I import the necessary libraries. I define these model parameters. I have some simulation parameters. I define these matrices in the state space model using the state space function. And then I can use the LSIM function in order to simulate the function. And then I can plot it. And let's just run this code. And as you see, we get the same results as in the previous examples. So now I have defined the mass spring damper system in 3 different ways. And I have used 3 different methods and 3 different Python libraries in order to simulate the mass spring damper system. In the next example, I will find a discrete version of this mass spring damper system. So we have, as in previous example, we have the following differential equations. We can use something called Euler in order to find a discrete approximation of these differential equations. And the Euler approximation is like this. The approximation to the x derivative equals to x plus 1 minus x of k divided by ts, which is the sampling time, and k is in this case the discrete timestamp. So if we take this approximation and replace the derivative of x1 on x2 with this approximation, we will get the following system. And let's just make it a little bit more cleaner. Then we end up with the final discrete system of this mass spring damper system. So we have x1 k plus 1 equals to x1k plus ts, which is the sampling time, x2k, and x2k plus 1 equals to minus ts, k above m multiplied with x1k, etc. So these are 2 discrete versions of these differential equations that we are going to implement using Python. We can also set this discrete system on a discrete state space form. So we have these two discrete differential equations, and then we can set it on the following discrete state space form. And this gives the following system as denoted here, where we have the discrete version of the A matrix and the discrete version of the B matrix. So let's implement this system in Python. So here you see the Python code for this system. I implement these two equations, as you see here, inside a for loop. So x1 k plus 1 and x2 k plus 1 inside a for loop. And then when the simulation is finished, I just plot it using the matplotlib as in previous examples. And here is A11, A12, etc. And B1 and B2 is this A matrix and the B matrix. And rest of the code is very similar to previous examples. I just define these model parameters C, K, M, and F. So let's also implement this code in the Spider editor and simulate it. So now we are back in Spider. I have implemented the necessary Python code. I import the necessary library, which is in this case just NumPy and matplotlib. Here is the model parameters, some simulation parameters. Here is the initial values for x1 and x2. Here is the A matrix, here is the B matrix, and here is the two discrete equations for this discrete version of the mass spring damper system. And then I plot it as, which is identical as the previous examples. Let's just run this simulation, and as you see, we get the same results as in the previous examples. So this blue one is x1, the position of the mass, and then this orange line is x2, which is the velocity or speed of the mass. So in this tutorial we have found the differential equations for this so-called mass spring damper system, which can be sketches like this. We have a mass, a spring, and a damper, and then we apply a force to this mass in order and then we simulate and see what's happening with the position x and the velocity of this mass. We have simulated this system in different ways. We have started by using the SciPy and the built-in OD solvers. We found the state space model of the system, and we implemented the state space model in two different ways using two different Python libraries. And then finally we found the discrete version of this mass spring damper system and we simulated it. So basically this is how we use Python in order to simulate differential equations in general, and we have used this mass spring damper system as an example. So that's all. So if you want to learn more Python, take a closer look at some of my additional other Python resources. At this location you find my Python textbooks. You find lots of videos and practical Python examples. So that's all. So good luck with your Python programming. Thank you.